my next story, which is this asteroid, which was actually discovered in several years ago, so hence its name, 2015 BZ509. And these two images were images of two separate pictures taken of the sky. And when you blink between the two of them, this object moves. And so that's how you can tell that it's not a star, but in this case, it turns out to be an asteroid. And what's exciting about this asteroid is that it turns out in the paper that I will discuss, there is evidence that this asteroid did not originate in our solar system, but actually formed around another star, but was captured by our sun. And it has been orbiting in our solar system ever since its capture. So this is kind of like an interloper asteroid, and that makes it pretty exciting too, because it's something from another solar system, and where the conditions for its formation and its original environment were very different from the environment in our solar nebula, which formed the sun and our planets. And so just to give you an idea of get you to understand how we think, why we know this asteroid was from another star, let's just take a look at our solar system. So here is our inner solar system with the inner planets that include Earth and Mars and Mercury and Venus. And then from then out, we have Jupiter and the outer planets. And you might remember that the asteroid belt is between Mars and Jupiter. And currently we have over 500,000 objects that have been discovered in the asteroid belt. But it turns out that there are objects all throughout our solar system. And these objects, because they're relatively small, no more than a few hundred miles across, they can interact gravitationally with the planets. So every time that they pass a close enough to a source of gravity, like the planet Jupiter, which is the largest planet in our solar system, they can actually have their orbits altered. And in some cases, the orbits of these asteroids can jump around quite a bit. And so there's a group of asteroids known as the Centaurs, which are collectively called this because they, when they mathematically model the orbits of these asteroids, it seems like it can be relatively easy for them to have their orbits shifted around due to the gravity of mostly the giant planets, and especially Jupiter. But there are also asteroids known as the Trojan Asteroids, which actually orbit roughly where Jupiter's orbit is, but they actually either lag or lead Jupiter. So Jupiter is going in this direction, and so there are a bunch of asteroids about 60 degrees behind Jupiter, and then there's another set of Trojans about 60 degrees ahead of Jupiter. And in this case, this scenario, these asteroids are actually very stable. So just because they're roughly in the same orbit as Jupiter, meaning the same distance from the sun, and so they're orbiting at the same rate, and so they won't ever get close enough to Jupiter to be perturbed by Jupiter's gravity and have their orbits substantially changed. Now, one other point I want to make is that we're looking down towards the North Pole of all the planets, or most of the planets in this case. And so when you do that, the orbits of the planets are all counterclockwise, and it turns out that the spins or the rotations of the planets are also counterclockwise. So if we were to look down at the Earth and zoomed in, you would see the North Pole of the Earth, and the Earth would be spinning counterclockwise in this picture. Now, this asteroid BZ509 is very different from all the pretty much most of the other asteroids that are known, and that's because it actually doesn't orbit in the same counterclockwise direction, but it actually orbits clockwise, and it orbits roughly in the same orbit as Jupiter, and it's positioned in such a way that it appears to be relatively stable just like the Trojans. But what's very peculiar about BZ509 is that it's in what we call a retrograde orbit, meaning it's orbiting backwards relative to the rest of the solar system. And so here is a video showing those Trojan asteroids. Here's Jupiter's orbit. And then we're going to see the orbit of BZ509. Here it is. And so sometimes it does get close to Jupiter, but it, because the orbit is inclined or tilted, even when it gets close to where Jupiter is in its orbit, it's well above or below the plane of Jupiter's orbit. So the actual period of this asteroid is right around 11 years, so it's actually very close to Jupiter's orbit. And each time it passes Jupiter, Jupiter does alter the orbit by a small amount. And so even though it does have this weird orbit, it's actually uncertain whether this orbit is entirely stable, just because it does swing by Jupiter. And so what the authors of this paper did was they went and ran a computer simulation, or actually 1 million different computer simulations of what they call clones of BZ509. And the reason why they had to do so many is that the orbit of BZ509 is actually not totally well known. And so they had to basically run a range of different parameters. And what they did was they started out with the parameters as they know it for today for this asteroid, and then they ran the computer simulation backwards into the past. And so what they, so here is what happened after about 40 million years into the past. So out of those million clones of BZ509, most of them got ejected. So more than 900,000 of these clones got ejected from the solar system, or they ended up falling into the sun, and so you know that that's not realistic. So they ended up with about 43,000 of these left, and this is a plot of just what the orbital parameters of those 43,000 clones are, where you're looking at the distance that these asteroids are orbiting, and then an inclination and eccentricity, which tells you how squashed their orbital shape is. And then when they keep running it, if they go back 4.5 billion years, they go back to just around the time in which the planets have finished forming in our solar system. And what they find is that there are still about 50 or actually 46 of these clones left, and some of them are distributed pretty far out in the solar system, but there's actually this stable zone near Jupiter's orbit, and that's what this clump and this clump are. So about 27 or 60% of the simulations still show this region to be stable. And so that gives them very good evidence that this particular asteroid has been in that stable area for most of the history of our solar system. And so it obviously couldn't have formed there because everything in our solar system formed orbiting counterclockwise, like we saw. And so for this asteroid to have been in this stable spot for so long, it must have been captured from a nearby star, and it ended up being in that stable region and has been in that stable region ever since. And what's really exciting about this is that because we have evidence now for one asteroid that has an interstellar origin, it means that there might be others out there. So last year, many of you might have heard about, and I think we even talked about, this asteroid Oumuamua, which was discovered to have come from interstellar space. So when you look at the orbit of it, the orbit meant that it didn't originate in our solar system. And then we also have observational evidence that it was very much elongated, sort of like a sausage or a cigar. And so this was our first known interloper from outside the solar system. But now we have evidence that there's at least one asteroid that's been captured much, much longer ago, and it's still in orbit around our solar system. And there might be other asteroids that have the same sort of origins outside of our solar system.